六、五、四、三、二、一，点火。
Right now, 400 kilometers above your head, there's a space station that most people have never heard of. While the world celebrates SpaceX launches and Artemis missions, China has quietly built something that's making the International Space Station look like a relic from another era. This isn't just another space race story. It's about how the rules of orbital engineering just changed and almost nobody noticed. The International Space Station, a $150 billion monument to international cooperation. For over 25 years, it's been humanity's foothold in space, a symbol of what we can achieve when nations work together. But here's what they don't tell you in the press releases. The ISS is falling apart. Not catastrophically, but inevitably. Its oldest modules are approaching 30 years old. Air leaks have become routine. Critical systems require constant maintenance. And politically, the cracks are even deeper than the technical ones. Meanwhile, China's Tiangong space station finished assembly in 2022. It's 1/5 the mass of the ISS, but here's the twist. It might actually be more capable. When engineers look at Tiangong, they don't see a smaller ISS. They see a completely different philosophy of space architecture, one designed for the 2030s and beyond, not retrofitted from 1990s blueprints. So today, we're going to break down exactly what makes Tiangong different, why experts are calling it the most advanced orbital platform ever built, and why NASA and SpaceX might be facing a problem they didn't see coming. Let's start with something most people get wrong: size. The ISS weighs 420 tons. It has 16 modules. Its habitable volume could fit a 6-bedroom house. On paper, it dwarfs Tiangong's modest 77 tons and 3 modules. But here's where things get interesting. Despite being 6 times heavier, the ISS only has about 3.5 times more living space. Where did all that extra mass go? The answer is technical debt. The ISS is an architectural Frankenstein, built from components designed in different decades by different countries using different standards. The Russian segment can't communicate directly with the American segment without translation layers. Power systems designed in the 1990s struggle to support 2020's experiments. Every upgrade requires working around legacy hardware. Tiangong took a different approach. It's not smaller because China couldn't build bigger. It's smaller because they designed for efficiency from day one. Here's a perfect example. The ISS needs external robotic arms like Canadarm2 to capture visiting spacecraft because its docking systems are spread across incompatible modules. Tiangong's core module, Tianhe, was designed as an integrated hub from the beginning. Everything docks directly. No external robotics required for basic operations. But the real genius is in the propulsion system. The ISS can't move itself. When orbit decay pulls it lower, Russian Progress spacecraft have to push it back up, burning tons of fuel shipped from Earth. Tiangong has ion thrusters built into its core structure, Hall effect thrusters that use electricity instead of chemical fuel. The result? Tiangong can maintain its own orbit indefinitely using only solar power. No resupply missions necessary. Think about what that means. The ISS is dependent on external life support at the most basic level. It can't even stay in orbit alone. Tiangong is self-sustaining. One station feels like it was built to need constant help. The other feels like it was built to survive on its own. And we're just getting started. Now let's talk about what keeps everything running: electricity. The ISS has massive solar arrays. 8 wings spanning 73 meters tip to tip, generating up to 120 kilowatts. That sounds impressive until you look at where the power actually goes. Here's a number NASA doesn't advertise. Only 45% of the ISS's electrical power goes to scientific experiments. The rest? Heating, cooling, maintaining outdated systems, and compensating for efficiency losses in 25-year-old hardware. Tiangong generates less total power, around 27 kilowatts, but it dedicates 63% to science payloads. How? Gallium arsenide cells instead of silicon. steerable arrays that track the sun precisely instead of fixed panels, lithium-ion batteries from day one instead of retrofitted after 20 years, and a thermal management system that doesn't waste energy fighting itself. The result is counterintuitive. The smaller, newer station actually runs more experiments than the aging giant. Tiangong currently hosts 25 fully equipped science racks. The ISS has around 30, despite being 6 times the mass. But here's the detail that blows engineers' minds. Tiangong's exterior mounting points can hold 67 external payloads. The ISS has space for maybe 20. Why does this matter? Because the most valuable real estate in space isn't inside a station, it's outside. Telescopes, particle detectors, materials experiments, all of these need direct exposure to the space environment. When you factor in external science capacity, Tiangong actually has more experimental volume than the ISS, despite being a fraction of the size. That's not just efficiency, that's next-level engineering philosophy. One station maximizes internal volume, the other maximizes science output. In orbit, that second approach might actually be smarter. Let's talk about something that doesn't make headlines but should: automation. The ISS requires near-constant communication with mission control. Ground teams monitor life support, manage power distribution, coordinate experiments, and plan every spacewalk in excruciating detail. Astronauts can't sneeze without Houston knowing about it. This works fine in low Earth orbit where signal delay is negligible, but it's a fatal flaw for deep space. When you're on the Moon, there's a 2.6-second communication delay. On Mars, up to 22 minutes one way. You can't run a Mars base the way we run the ISS. It's physically impossible. Tiangong was designed with this reality in mind. Its systems are far more autonomous. Example 1. The robotic arms. The ISS's Canadarm. 2 requires ground operators to control virtually every movement. Tiangong's 10-meter robotic arm can execute pre-programmed tasks independently. It can literally crawl across the station's exterior by itself, relocating between attachment points without human guidance. Example 2. Life support. When the ISS's systems detect an anomaly, alarm sound and ground control investigates. Tiangong's systems include AI-driven diagnostics that can identify and often fix problems autonomously. This isn't about replacing humans, it's about reducing dependence on Earth. Because if you want to build a base on the Moon or Mars, you need systems that can keep people alive even when communication is cut off. And here's the truly clever part. Tiangong's Wentian module contains a complete backup control system. If the main Tianhe core module fails catastrophically, Wentian can run the entire station independently. The ISS doesn't have that redundancy. If certain critical systems fail, the station could become uninhabitable within hours. One station was designed assuming Earth will always be there to help. The other was designed assuming Earth might not be able to. That's not just an engineering difference, it's a philosophical one about what space exploration really means. Okay, let's address the elephant in the room. The ISS has produced decades of groundbreaking research, thousands of experiments, Nobel Prize-worthy discoveries. Isn't that what really matters? Absolutely. But here's what's less discussed: what kind of science each station prioritizes. The ISS has primarily focused on understanding microgravity itself, how flames behave without convection, how proteins crystallize without gravity disturbing their structure, how the human body degenerates in space. This is important work. But notice what it's not optimized for: preparing for permanent life beyond Earth. Tiangong's research agenda is different. Yes, they're studying microgravity physics. But look at what else they're doing. They've successfully grown rice seedlings through complete life cycles in orbit. They're testing closed-loop ecological systems where plants recycle waste into oxygen and food. They're studying how Chinese medicine responds to microgravity, relevant because herbs are easier to grow than pharmaceutical factories on Mars. This isn't curiosity-driven research, this is infrastructure research. They're systematically answering the question, what do we need to survive somewhere there's no Earth to send supplies? And then there's the Zhentian Space Telescope. Scheduled to launch in 2026, Zhentian will be a Hubble-class observatory with a field of view 350 times larger. But here's the innovation. Unlike Hubble, which required dangerous space shuttle servicing missions, Zhentian is designed to dock with Tiangong for routine upgrades and repairs. Think about what that enables. When a component fails, you don't abandon the telescope. You bring it to the station, swap parts, and redeploy. Hubble required billion-dollar rescue missions. Zhentian maintenance becomes routine. The ISS never integrated this capability with its external science assets. Tiangong designed it from day one. Here's the pattern. The ISS studies space. Tiangong prepares to live there. And if your goal is permanent human presence beyond Earth, the second approach might matter more. But we need to talk about the geopolitical implications because this is where things get really interesting. The ISS was built on a simple premise: space unites us. Americans, Russians, Europeans, Japanese, Canadians, all working together despite earthly tensions. That vision is dying. Since 2022, the partnership between NASA and Roscosmos has been held together with duct tape and diplomatic niceties. Russia has repeatedly threatened to withdraw. The U.S. has explored options to maintain the station without Russian cooperation. Neither side trusts the other. Meanwhile, China is quietly building something different, not a cooperative station like the ISS. An alternative. They've invited Pakistan to send experiments. Egypt has signed cooperation agreements. Venezuela, South Africa, Kenya, nations that never had access to the ISS, suddenly they're being welcomed to Tiangong. For these countries, this isn't about science, it's about dignity. For decades, space was a club controlled by the West and Russia. Now there's a third door, and China is holding it open. This is the same strategy China used with the Belt and Road Initiative. Offer access to countries historically excluded from Western systems. Build influence through opportunity, not coercion. And it's working. By 2024, over 30 nations had signed space cooperation agreements with China. Compare that to the ISS's 15 partner nations, many of whom are questioning the partnership's future. Here's the uncomfortable truth. While the U.S. debates whether to extend the ISS to 2030 or let it burn up in 2028, China is building the relationships that will define who has access to orbit in the 2030s. When the ISS retires, there will be a gap. NASA's commercial station partners like Axiom are years away from operation. Russia's proposals exist only on paper. But Tiangong will be there, operational, expanded, and politically aligned with half the developing world. The question isn't whether China's space station is better technically. The question is whether the West just lost its monopoly on orbital diplomacy without realizing it. Now let's talk about NASA's response, or rather why they might be looking in the wrong direction. The Artemis program is going to cost over $93 billion to return humans to the Moon. The Space Launch System rocket costs $4.1 billion per launch. The whole architecture requires orbital refueling, lunar gateways, and coordination between dozens of contractors. It's ambitious, it's expensive, and it might be solving the wrong problem. Because while NASA pours resources into flags and footprints lunar missions, China is solving the harder question: how do you live somewhere permanently? Artemis is designed to visit the Moon. China's lunar program is designed to stay. Their proposed International Lunar Research Station, developed with Russia, isn't a HAB module and a flag. It's a plan for robotic precursors in the late 2020s, followed by crewed facilities in the 2030s, building toward permanent presence by the 2040s. And here's the kicker. All the systems they need, they're testing them right now on Tiangong. Every closed-loop life support system, every AI-driven automation protocol, every long-duration habitation lesson. They're learning in orbit what NASA is still planning on paper. Meanwhile, SpaceX promises that Starship will change everything, and maybe it will. But Starship's goal is to move mass cheaply. That's the easy part. The hard part is keeping people alive once they're there. China isn't racing to plant flags. They're building the boring, unglamorous systems that make permanent habitation possible. We don't need more rockets. We need better life support. And when history looks back, that might be the defining difference. NASA is designing missions. China is designing infrastructure. So let's answer the question we started with. Which space station is better? If you measure by size, age, or legacy, the ISS wins. It's a monument to what international cooperation can achieve. It's trained generations of astronauts. It's advanced our understanding of space immeasurably. But if you measure by efficiency, autonomy, and future readiness, Tiangong isn't just competitive. It might be superior. It's smaller but more focused, newer but built on lessons learned, nationally controlled but increasingly internationally accessible. And here's what should concern Western space agencies. Tiangong represents a philosophy. Space infrastructure doesn't need to be massive. It needs to be smart. It doesn't need to be cooperative. It needs to be resilient. While NASA and SpaceX chase spectacular achievements, lunar landings, Mars missions, reusable rockets, China has quietly built a functioning orbital home, and they're using it to prepare for what comes next. The ISS will retire this decade. When it does, Tiangong might be the only game in orbit for years. That's not a failure of American technology. It's a failure of American strategy. Because the real space race isn't about who gets to the moon first. It's about who builds the systems that let us stay. And right now, while we argue about budgets and contractors and billionaire space tourists, China is answering that question with hardware that already works. So maybe the title of this video is wrong. Maybe it's not about which station is better. Maybe it's about which one actually prepares us for the future humans will live in space, not just visit. And by that measure, Tiangong isn't making NASA look outdated, it's showing us what they should have been building all along. If this changed how you see the space race, hit subscribe. We're covering the space stories the mainstream media misses, from Chinese lunar programs to the real costs of Artemis. And drop a comment, do you think Tiangong's approach is the future, or is NASA's bigger is better philosophy still the right path? Because one thing's certain, the next decade in space is going to look very different from the last. Thanks for watching.